Let in Robert. Hello, Robert.
Good morning.
Oh, Angela.
Bad traffic today?
Hello, Angela. Yeah, another one of those. I mean, the tunnel today, I don't know what happened.
I don't know, last week, like a pole fell on Monday, like a pole fell on the GWB or something like that. Yeah. I don't know.
I don't know what it is about rain and people forget how to drive when it
There's more relief, California.
yeah.
It never rains in California, so the one time it does.
That's funny about California. I lived out there for a couple years, and in their winter is very mild. It's like I work in Celsius, so let me see what it will be like. Their winter is like 50s Fahrenheit, right? And in the winter time, we had Lily was a baby, so we would have to take her outside even in the winter, and the people there would show up in parkas, which I thought was pretty funny because it was it's like spring weather.
That's the only time they had to wear their parka.
And yeah, but it's still weird. It was such a weird thing to see. But yeah, I mean, I know that I almost ended up taking a job in Tempe, Arizona. And sorry, I will share my screen so you don't have to stare at my face. And
It's a nice 120-degree weather there.
yeah, so the thing the guy told me, he said that the skin, if you live there long enough, your skin actually recedes because of the arid climate, and you actually like when you go somewhere out on the East Coast, you feel incredibly uncomfortable, which is interesting. The body will actually have physiological changes.
Yeah, my cousin lives in Vegas, and he basically
Oh,
has like 1,000 moisturizer
He's-
bottles. He's just it's so dry there all day.
Yeah.
Just moisturizer.
That's the one. Yeah, that's the thing about California, where there is, yeah, the dryness. Really, we noticed it. So the one is it working yet? One benefit, and I don't know how this is related to machine learning, but it's still fun for me to talk about, is that the humid climates lead to oily skin, which ages you less apparently. So if you go out west, people live out there, they age, you see it because of the lack of moisture in the air. So there you go. You can't have everything. I guess you got to pick what you want. You want to not experience days like this 100 times a year, or you can have accelerated aging.
It's very much 100 times a year. They got the age is awful.
I feel like we've had a really rough like last month of climate weather-wise. So first of all, apologies for the late start. We have an abbreviated lecture today, but that's all right because we've already covered a lot. I think I'll close the door. What I want to cover today two things. One is to finish the slides on Deep Learning 1. And if I have time, I'd love to show you an example. I found an example online of I was looking for the most simple, the most minimal example of a working neural net in Keras, which if we have time, I will show you. So I think this is where we left off last time. I guess right. So one thing to keep in mind is that the only difference, as with all supervised learning, the goal of the neural net is just to map your feature vector X into the label Y. And
Professor, if you want them to see you, you have to stop sharing.
all right, yeah. I need to hire a cameraman, I think, and then also a Zoom operator. Is that too much to ask the department?
I think for a class of 10 people makes sense. Have
Yeah,
two other people
I think
work
so. I think it does. I think you're right. Right, so the goal of the neural net F is just to map our feature vector X into Y. And remember that we're starting off with just a training set of X, Y pairs, N of them. And so the only difference between, a logistic regression your F, this was something like, it was a simple function that you could write. This was our logistic regression. And that's our shallow learning. And I don't know how to write the deep layer. I mean, I could actually try. So it'll be something like, so the only thing about a deep net is that you have your first layer, call that W1. And then that gets passed through your nonlinearity, and then you have another linear, and then you have another set of weight vectors, and then that gets passed to a nonlinearity, linearity, etc. And so I could actually extend this, and maybe I will. You could just keep going with this. This is sigma, and then this will be W3 transpose that. And so what's interesting about this is that what you notice is that you're factorizing. Essentially what you're doing is you're factoring or factorizing. I don't know which one of those it is. Let's say, lots of letters here. Let's say D of C of B of A of X. Right, so you're basically taking a function and you're trying to represent a complicated function with a factor, with a product, of simpler functions. And so each one of these factors is basically a layer. And so I guess the insight in deep learning is that, let's say let's say that each of these nodes is a degree of freedom. So think of it as like think of it as a parameter. If you have a fixed number of parameters, it's better to organize them in this configuration rather than putting them all into a single layer. And the reason for that is if you have a shallow network where all your nodes get put into one layer and then the output comes after that, that has been shown both mathematically as well as empirically, and mostly empirically, frankly, to not generalize as well. And so I wanted to write something on the board, but I just switched. So maybe I think I have a little, yeah. So this is an image, whatever, a diagram, a drawing that when I first looked at, I was confused, but I actually think it's pretty clever. So this is from the Goodfellow book, the Deep Machine Learning Bible. So here you have a data set. The red circles are one class, the blue crosses are another class. And they lie on a plane, which is often called a manifold. So a manifold is just, you can think of it as like it's just any subspace. It's any portion of a high dimensional space. So one thing that is strongly believed to be true is that if you have if you take a picture of a natural scene, and let's say you take many pictures of natural scenes from all over the world, and let's say your picture that every picture is 100 pixels by 100 pixels, and so that data of image intensities, of pixel intensities, lives in a 100,000 dimensional space. However, the scenes of natural footage will not actually span that 100,000 dimensional space fully. Why? Because there's certain structure in natural scenes that will make only some portion, some spaces of the 100,000 dimensional space be occupied by the data. And so the idea here is that this napkin here, this sheet of paper, is like your manifold. So this is your data is lying on this two-dimensional manifold, and you want to separate the blue from the red. And so one way of doing it would be, you know, this decision boundary does a great job, right? And you can learn it. It is possible to learn it, you know, just by, you know, working with a, you know, just a single layer that tries to learn this boundary. However, and so just basically tries to learn the function in one shot. What deep learning is doing, though, is what stacking of the hidden layer does is effectively making these folds. And so if you fold this napkin a few times, what you end up doing is that you end up achieving a much simpler decision boundary. And so every time you fold the napkin, you're making a decision. Is the data, you know, which side of that fold is the data point on? And by doing that a couple times, you end up with a function that's easier to learn. That's the key. This is what this picture is trying to communicate is that decision boundary on the right requires less data to learn than the decision boundary on the left. Even though mathematically it is the same function, right? But learning that requires more training data than that. And so adding parameters vertically is a good idea. So a single layer with 100 units is worse than, let's say, 2 layers of 50 units, etc. And the reason for that is because, you know, the functions, the true functions that generate the data that you're working with in the real world are believed, you know, we believe that the functions truly have this factorial nature. So let's say whatever the process is that generates MRI scans of benign versus malignant tumors, right? There's a generative process there that maps from the underlying, you know, anatomical structure to the set of image MRI voxel intensities. And so that process is obviously very complicated, but, you know, the field of deep learning is saying, let's model that process as a product of simple functions rather than one complicated function. And so again, this is done despite the fact that in theory, because of that universal approximation theorem, you can learn any function in theory with just a single layer, provided you give it enough hidden units. Okay, so I think I've said this before, so I don't want to spend too much time on it, but this is really, I think, important, or kind of it's an intuitive feel for why deep learning has emerged and has solved a lot of these difficult problems that the human brain has solved, over evolution, but computers only recently were able to handle. And those again are object recognition, natural language processing. There are others that I'm blanking on. But the idea is that every, at the lowest level, you have a set of pixel intensities corresponding to the picture of the man sitting. And trying to learn man sitting from these from this vector of pixel intensities would be, a very difficult task, right? There's just it's very hard to see how you can get that kind of semantic content from just a vector of integers, because pixel intensities are just, images are like, for example, they're represented by either, if it's grayscale like this, a number from 0 to 255, and if it's color, you have 3 numbers that are 0 to 255. RGB, or it doesn't have to be RGB, but RGB is one of those color bases. And so it's very hard to see how we can map, a vector of integers into man sitting. And so what deep learning does is it tries to break it up into stages. So you have groups of pixels that are connected, and those will be your edges, and then you have groups of edges that will be your first hidden layer, and then your second hidden layer would be a combination of edges, which is a contour, and then you have your third hidden layer, which would be your combination of contours, which would be your objects, and that's how you can go from a set of grayscale image intensities to a caption such as man sitting. So captioning images is one of these really important problems because, for example, Google Images or any kind of database of images, all these images that users submit onto the internet, you want to have a way of labeling them, of grouping them, and we don't want a human to have to do that. And so assigning a text caption to an image is actually a very difficult problem. And again, this deep learning has been used for that purpose. I mean, it's a difficult problem, I think, on a number of fronts. That it's not like, it doesn't map neatly until like X has this many numbers and Y has this many numbers. Like images have different sizes, captions have different length. And so it's a really challenging problem. And I think that there's been a lot of progress made on it, although it's not really my specialty. We've done this already. We did the XOR problem. So I'd like to move on to how learning is actually done. And so I'm not in this course, I don't cover the mathematics of stochastic gradient descent, but I do at least want to make you aware of the basic idea. So you do need to define a cost function. So what is a cost function? It's something that quantifies how good a model is at classifying your training data. So that's one thing. So that's your cost, and that's typically denoted with a J. And then you have your model, which is generally represented with theta. And so theta is a long vector, and the theta vector consists of every parameter, every W in your neural net. So for the XOR problem, theta would have had, we had a 2x2 matrix, which was capital W, so that's 4, and then we had the lowercase w, that was 2, and then you had all the offsets. So theta there would have had, I guess, nine parameters. So you're just stacking all the free parameters of your neural net into theta. And then what you do is you compute the gradient of your cost function with respect to theta. And why did you do that? Well, why? Because, you know, again, going back to Newton, who figured out that if you want to minimize a function, so we want to minimize the cost, we want to compute its derivative, set it to 0, and solve for theta that minimizes j. And so I thought that before I move on to, because the next slide is going to show you, I'm going to stop sharing up because I want to give you a concrete example of this. So I'm trying to strike a balance between not burdening you with mathematical formalisms, but at the same time, I don't want to be so superficial that you're left kind of feeling like this is all nebulous and vague. And so what is it actually? What is it that you're doing? And so what I thought I would do before I go into something called the cross entropy loss, I'm going to start with a simple example. So first of all, this is your training data. And what's really important is that all of this stuff, everything that I'm saying today about learning, how learning is done, it's all done on your training set. And the assumption that is typically made is often termed IID, which stands for independent and identically distributed. So that's important. So in IID training data is the big assumption in all of machine learning as it stands. And very recently, there have been so the training data is assumed to be independent and identically distributed. What does that mean? So let's say, let's just take the example of a Gaussian distribution. And so it has some mean and it has some standard deviation. And so you can sample that Gaussian distribution n times. And so then you'll have a set of numbers. X1s, they're just scalars here. And so this set of numbers is independent and identically distributed, which means that if you take the mean of these numbers, they'll approximate mu. And if you take the standard deviation, it will approximate sigma. And so that process of, basically every time you get a sample, that sample is coming from the same distribution, and every draw is independent of the other draws, right? So there's no correlation here between the x's. So in machine learning, it's not just an x, it's an x comma y. So you can think of x comma y as just like, it's just a vector, because x is a vector and y is a scalar, but you can bundle it in with x. And instead of having a d-dimensional vector, you have a d+1 dimensional vector. And the idea is that and that there is some underlying distribution, say P, that generates your data. And the idea is that your training set is coming from that one distribution, and every example is independent from the others and identically distributed. So what I'll say is that the independence assumption is not really a problem, right? If you're a doctor or radiologist and you collect, you get MRI data from 100 or 1,000 patients, it's totally valid to say that those 100 to 1,000 scans are independent. There's no reason to believe, that there's any kind of relationship. Although I guess if you're in a geographic location, maybe, I don't know, or if certain scanner parameters, things like that. But that's it. I don't view that as the problem. The bigger problem is the identity distributed. That that's the assumption that is violated most often in machine learning. And so let me think of, well, like self-driving cars, I think, are a good example, I think, for this. So teaching a self-driving car how to learn how to drive, and that is obviously very complex. And let's assume that the inputs are let's assume that we're taking the Elon Musk approach, which is no radar, no sonar, none of that. We're just going to do images. We're just going to do video, just cameras everywhere. And so we have a really good representation of the visuals of the visual environment. And the way these things are learned, presumably, is that they drive around. They have they drive around and they collect a whole bunch of data, whole bunch of video data from what it's like to navigate along a road, highway, etc. The problem is that Teslas are going to be driven everywhere, not just where they obtain the training data, and so they don't control they don't control where their customers are going to end up using the car. And so there's this big generalization error or generalization noise that comes into play, because your training data, so the distribution of your training data is not going to be the same as your test data. And it's even possible that within your training data, like if you collect some data from driving around San Francisco and another part of the data from driving around New York, you're going to violate that assumption. So this identity distributed assumption is often violated. And I think what you're going to see in the next 10 or 20 years of machine learning is we're going to stop, not we, the field, the royal we, is going to stop coming up with algorithms that assume this. And the algorithms are going to explicitly account for the fact that your data is coming from multiple different distributions. Okay, and so nevertheless, everything I'm saying today and everything you see in a textbook makes this assumption. And so the easiest cost function, I think, to understand is the mean squared error. So I'm just going to call it MSE. And I'm going to say that it's just the difference between y and its prediction. I'm going to square it. Why do I square this? Why do I have to square this? Exactly. So positive and negative don't cancel out. Follow-up question. Why don't I just do absolute value then?
Isn't there a cost function that's just absolute value?
Yeah. So why is this not a good idea? Or maybe it is. Do you think it's a good idea? Why is the absolute value of y minus y hat not a good idea for a cost function? Why is like the whole field of telecommunications, machine learning, everything always use this y squared? Why not absolute value? What was on the slide right before I switched to what was the slide about before I switched to the board? The gradient. And so what can you say about the gradient? Let's say you want to differentiate this versus this. Which one of them is going to be easier to differentiate? The square, right? Because of the fact that differentiating quadratic is nice. It's convex. Whereas this thing, well, it's still convex actually. Absolute value is still a convex function. The problem is this. derivative at 0 is not defined. And so you can't, there's no way to differentiate J if you're using the absolute value. And so I've left myself room. This is basically going to be a summation over a training set. So the mean squared error loss, which is a good loss function if your y is continuous, it's trying to minimize this thing. So this is the truth, and this is what your model predicts. And you want to make the prediction as close as possible to the truth on the training set. And let's say that, and what you have, the last thing I'll write here, maybe not the last thing, is that you have the y hat is a function of x of n, and that's how. So your loss function and your f is the thing that you're trying to, that your f has parameters that you're trying to pick to minimize this thing. And so what you end up doing, you basically have, if you want to take the derivative, maybe I'll explicitly put in data here. This is a semicolon. I know I've been told my semicolons are not very clear. So, just so you know. And so the derivative of this, partial derivative, is going to be so that's, whatever f is, we're gonna, because of the chain rule, this is going to be the expression for the gradient of the cost function that we're gonna want to set to 0. And for example, for linear regression, this thing leads to like a formula. There's like a closed form formula where you can actually figure out what the theta is. So if fx of theta, sorry, it's just a linear function, something like this, then the optimal solution ends up being something like, sorry, silence my phone for a second. You may have seen this equation before. This is called this isn't deep learning. I'm just putting it on the board. It's kind of an aside. This is called the Moore-Penrose pseudo inverse. So to solve a least squares problem, you can use the PINV function in MATLAB or the backslash operator. So I'll do the same thing. And X is a matrix, Y is a vector. So X is a matrix of all your data points stacked together, and Y is just a vector of your target variables. So I put this on the board because I wanted to give you, before I show you the loss function that is, oh, Siri, I don't want to do that now. Before I put on the loss function that is commonly used in classification, which is a little bit less intuitive than this, I wanted to show you the idea of gradient descent with mean squared error. And so with gradient descent, in many cases, you can't solve. So this is the equation that you want to set this to 0. You want to find the theta that sets this to 0. And the problem is that with very few only on a few exceptions, like a linear regression, you have a closed form solution. In every other case, in all practical cases, you have to find theta numerically. And so now I'm gonna switch back to the slide because the slide has a picture of, right. So this is the J, the contours of this function here are the J. And so the idea is that you're trying to get to the bottom of J. And to get to the bottom of J, you need to be able to figure out the gradient of this bowl at every point, right? So I think one thing that confuses people is that the gradient is a function. It's a function of where you are in the space, right? So it's a vector. And the magnitude of that vector, I think, is less important than the direction. The direction of that vector is really important because the direction of that vector points in the direction of steepest descent, and that is a really. It's actually, I had my what did she teach me? Mathematical foundations when I was a grad student. And she poses a question to us. She's like, why, she asked, why is it that the gradient points in the direction of steepest descent or steepest descent, depending on whether you're minimizing or maximizing? And it's actually not, there's a simple proof for it, but it's not, I don't think it's intuitive that if you have, I'm running out of board space and okay, I'll just write it out quickly. Sorry, if you have fx of y, okay. I will, let's see, what can I erase here? So the question I'm posing is why, let's take the simplest case. Why is it that the gradient points in the direction of steepest descent? And so let's say I have a two-dimensional, let's say I have just a two-dimensional function, and let's say keep it really simple, x and y. And I have some function defined over x and y. And the idea is that I want to know what the gradient is at some arbitrary point. And what the gradient of f, right, I'm going to write it as a row vector. In this case, it has only two elements because there's only two dimensions. So at every point, I differentiate the function with respect to x, and I differentiate it with respect to y, right? So this is the slope of the function going this way. And this is the slope of the function going this way, right? So I'm at a point, and I evaluate the derivative both ways. And what the gradient is doing is that the resulting, it's a vector, right? There's going to be some magnitude of change going this way and some magnitude of change going this way. And if I go in, in the composite direction, if I go, then I'm guaranteed to be taking a step in the direction where the hill has the highest slope, or where the hill has the highest slope, which to me is not immediately intuitive. That if I just measure the slope one way and I measure the slope the other way, and I take those two numbers. So basically, one way of thinking about it is if this number is much larger than this number, right? If the rate of change in x is higher than y, then I probably want to go in the direction of x, right? So if this is 0, for example, and this is 1, then I definitely just want to keep going in the direction of x if I want to minimize this function. But it's less clear that if this is 2 and this is 1, then I want to go, whatever the arctangent of 1/2 is or whatever, right? So that it's a really, for me at least, because I'm weird, I like to think about why it is that the gradient does in fact take you, following the gradient does in fact take you in the direction of the sharpest change. And I think I was telling you guys, fruit flies do this, dogs do this. They essentially go in the direction of the gradient. And that's like very simple nervous systems have figured out this kind of procedure. I've computed, obviously not with equations. In the brains don't compute equations. The brains don't solve physics equations. I remember reading an article a long time ago about how David Beckham is a genius because he solves, with free kicks, he solves very complicated differential equations but I mean, that's a crazy statement, right? His brain is not, first of all, he's definitely not doing it, whoever he is, but even his brain is not doing it. His brain is, I mean, I guess effectively, yes, you can argue that there's an optimization of like his foot angle and everything, velocity, whatever, all the factors, but it's not, the differential equation is like, has been brought as a model of that process by humans. I don't think the brain is Bayesian. I don't think the brain is solving any mathematical equations at all.
Just to
Yeah.
cool for a second, I would argue that is kind of, it could be that that's what we do because we learn it over time. Like in the way that you train a model, and that if Beckham went to the moon, for example, it would
Right.
take him a very long time to learn how to kick to accomplish the same thing. Right? His brain have to like relearn it. So in
Right.
the same way, like I don't let's say understand like the layers that like program machine learning, so all those layers they all mean.
Yeah.
My brain learns that over time as I get more data. Practice.
Yeah. I get, yeah, right. I agree. I totally agree with what you said. I guess what I'm saying is that, like, I don't, and this is kind of like a philosophical debate in a way. I don't view that. I feel like what humans have done with mathematics and modeling physical processes I don't think that's, I think the brain they are solving a problem over time with experience, like you said. I just don't think they're actually, well, they're not aware. I don't even know if it's, I don't even know the equations are in there.
I think it's the opposite, actually. Equations are man-made descriptions of what we experience. So equations are our way of trying to approximate the brain, not that the brain approximates equations. Like that wouldn't make any sense. They're like, math,
Right,
math is a man-made construct.
Yeah.
Like, to describe what we see and experience, and that's why there are assumptions and flaws. It doesn't always work.
Yeah, I guess.
It's
Yeah,
way more
but I'm saying,
philosophical.
no, yeah, but I don't think that, no, but like, the question is, like, is a fruit, like, if a fruit fly has figured out how to fly to go in the direction where the odor is getting strongest, is it actually computing a gradient of the odor concentration with respect to space, or is the circuit that implement, because there's some circuit, right, that does it. There has to be. There's a circuit where the inputs are the sense organs, which is olfactory here, and the output is like the motor, whatever the fly. I don't know anything about flies, about how they have to figure out how to orient themselves to get in that direction. And I guess I have a hard time seeing. I think that what they're doing is kind of like a hack, I guess is what I'm saying.
I think we talked about this in a while, like consciousness and mind versus brain.
Yeah.
I hear it.
But anyhow, it's interesting to think about, because is David Beckham a physics genius, or is he just have really good muscle memory and he's able to replicate the same pattern of sequence of movements really well, right? Because that's all. I think that I don't know. It's interesting for me to think of. Maybe he is. Maybe David. Maybe I just hate you for being so handsome and wealthy, and I'm just taking out my frustration in this class. Maybe you are a physics genius too. Yeah. Right. So I showed you the mean square error loss, but for classification, that's not what is done, and because if y is discrete, this is a bad idea. You don't want to minimize the square error when y is 0 or 1. Oh, I haven't checked. Oh, what? And now we go viral. about it. Okay. Right. So, right. So cross entropy loss, and this is right. This is something that has confused me. So I'm gonna try to do my best to explain why. So first of all, this cross entropy loss is a measure between two distributions. And so P and Q, you can think of them as one dimensional. You can think of those two Gaussians. And this all comes from the work of Claude Shannon, who invented information theory. And so this note, I really like the notion of entropy because it's like one of the few things that cuts across different disciplines. Like there's there's a thermodynamic entropy and there's a statistical entropy, and the two are really, really closely like there's a very clear link between them. And the link is basically disorder. So, the reason that in a closed system, the system will go to maximize entropy, it will maximize the disorder. And statistically, what the analogy is that if I have I have to write another equation on the board. Sorry. So first of all, what is entropy? Before we get into cross entropy, what is entropy? And I probably should have included that at the slide. So this is really interesting. There's this notion of surprise. So this came about during the time right before the Second World War, when there was like an arms race to try to figure out how to decipher each side's encrypted messages. And this notion that came up of entropy of a distribution. And so what it basically is the integral. This is another thing that has really, this is natural log. It's basically, I think there's a negative sign here. I'm going from memory. And so it looks weird. So first of all, just as a to orient you, so the mean is just the mean of x. I'll write it as it's just this. So this is the mean of x. It means that this is a weighted combination of basically if x has, the simple case, if x only has 3 values and it looks like this, x can be -1, 0, or 1, and this is P1, this is P2, and this is P3, then the mean here would just be equal to -P1 plus 0 plus P3. Okay, so whatever that, whatever, it will be negative the height of this stem plus this stem. So the idea is that you are, for every possible, again, P of x is just a distribution. Think of it as a Gaussian. So this is the expression for the mean of x. So entropy is the mean of ln it's the so if you look at it's helpful to actually see what this is. And so the idea is that the logarithm of a number that's very close to 0 is very large, very negative, and the logarithm of a number that's close to 1 becomes 0, right? So this is, if I have, it's negative, this will look something like this, I think. Hope I'm getting that right. So the idea is that what this equation is saying is that you can think of it as a measure of surprise, average surprise. And so the informative events are the ones that are low probability. And so that's kind of the basic insight of Shannon, is that information is information content of a message is inversely related to how probable that event was. And so when you are conveying something, when you are transmitting a message that had a very high prior probability, when you're transmitting the outcome of an event that had a high probability of happening, that's not a lot of information. But when you are conveying something that had a low probability, that's a lot of information content. So I'm trying to think of an example here but it's not coming to me. But the basic idea is that entropy is a measure of the surprise, and so this is a weighted summation of this. So basically, a distribution that has high entropy is going to be more likely to produce these surprising events. So that's entropy. And what the cross entropy, I'll go back to the what the cross entropy is doing is it's extending that notion. Instead of computing the average surprise of itself, it's computing the average surprise between P and Q. And so one way to understand this is that if I move my cursor here, I think the last thing I'll say today is the following, is that if you are trying to, let's say that P is the truth and Q is your model, you want Q to approximate P. And the basic idea here behind cross entropy loss is that this cross entropy becomes zero when the two distributions are equal. And so and otherwise it's negative. And so, and that's why the negative sign is there. So when P and Q are far apart, when the two distributions are very different, that cross entropy is going to be very, very positive because of the negative sign. So the P of X times log Q of X, this is always going to be a negative number because the log of a probability is always negative and P of X is always positive. And so the idea is that, remember I said at the beginning of the course, I really thought about, can I teach machine learning without invoking probability? And I really think it's impossible because, and I mean, this is a very good example of that. This is at the heart of all of deep learning, is this loss function. So the idea is that in deep learning, you are trying to find the distribution that best approximates the ground truth distribution. And this is the equation here that does that. I'm going to give you guys some reading material when I get back to my desk. I'm going to read it before the data challenge, okay, which is going to be released on Monday. And I look forward to seeing everybody back here in person on Monday at 9:30, 9:35 usually with me. Bye, guys.